I'm Freddy Francis. Welcome to this laboratory section of our course. So, as you would have seen in the video, this week is dedicated for optical amplifiers, and which is the most popular optical amplifier is the EDFA, erbium doped fiber amplifier. So, erbium doped fiber amplifier came into the forefront in the early 1990s, and it caused a rare revolution in the capacity of optical fiber or the capacity used in the optical fiber. So, as we know. A single wavelength can be amplified using a SOA, but EDFA has a very big optical bandwidth, so that multiple channels can be simultaneously amplified, which made WDM, wavelength division multiplexing, possible. So here we will see how an optical amplifier, that is the EDFA in this case, is characterized, and we'll see we'll do particular analysis on input and signal, the signal and pump characterization. As you can see here, this is the setup we are using. But before diving into it, I will give you a brief introduction of just a refresher of how the EDFA works. As we know, EDFA is a 3-level system. It has got 3 levels, and the pump, which is a 980, pushes the erbium ions from the ground state to the upper energy state, from where it non-radiatively decays to the metastable state, where it has a higher lifetime of around 10 milliseconds, and it will stay there for 10 milliseconds. By the time when the signal comes, it stimulates the emission, causing a stimulated emission at 1550, which is in the same phase as in a signal system, as a signal photon, so which causes the amplification. So this is how the EDFA works. You might have studied this well in the lectures previous to this lab recording. So in this lab recording, what we are focusing is how we will show you how an EDFA system is characterized, and how signal and pump saturation is studied. So I will start by introducing you to this particular kit. This kit is manufactured by Fiber Optica, which is called the light runner kit. So this box is the hardware part of it, and it is connected to this particular PC, and this is CPU of the PC. So as you know, it's slightly old kit. There is an updated version of this available. Now we'll take a closer look in the light runner kit. So here we have 5 lasers here. Each of them working at 1510, 1530, 1550, 1570. These are the IR lasers, and we have a 1660 laser here, which is the visible one. Okay, so this is the laser section, 5 lasers here. From here we will take a connection out. Each of them can go up to 1 milliwatt, around 0 dBm of power can be output out of each of them. And correspondingly we have detectors here. All of them are indium gallium arsenide detectors, 5 of them here. So PD1, PD2, 3, 4, 5. Last one is visible, which is corresponding to the 660 nanometer. And interestingly, all of these detectors are broad spectrum detectors, so they can detect from 1000 to 1700 nanometer, which means that all of these lasers can be detected by any one of these photo detectors. As we know, the photo detector converts the optical energy to electrical energy. So the electrical signal can be taken out from this BNC port here. You see the other optical components of the kit. Here we have the EDFA section. Here in this here you can see that there's a coupler here. There's a EDFA that is sitting inside the kit. So we have to take the output out of this coupler. It's a backward pumped setup we are using here. Now we have the mux here. We have the demux in this section. So mux and demux will be taught later. We are not using that in this particular experiment. Similarly, we have a circulator here and a coupler here, and FBG is provided here along with a variable optical attenuator, VOA. So these components are not used in this particular experiment. And there is a section for photodiode characterization. Again, you will see photodiode characterization, but probably not using this kit, but there is a provision provided in this kit for photodiode characterization. And in the other end we have the communication modules. As in, so here we have channel 1 output, channel 2 output, and the next channel trigger you can give here. and here we have three digital ports. This is a USB 2.0 port which is connected to the PC, another one USB 1.2 port which is also connected to the PC, and digital link which is also connected to the PC. So the information that is transmitted from here is basically the control information is to this kit, and there is a digital oscilloscope function available within the PC. So that digital oscilloscope information, the signals will also be passed to this particular link. So that's and then here is a modulation selection switch. So as we know, this lasers are not just continuous. They are continuous lasers, and there is a provision for modulating them also in this kit. So that can be done either externally or internally, and you can use a software control or a hardware control for that. So here is a section dedicated for that, and there is a section dedicated for laser characterization also. Okay, so these lasers can be characterized using that particular section. So this is basically the light runner kit which is produced by Fiber Optica, and we'll be using it for many of the upcoming experiments also. So this is the power meter we will be using. As you can see, it has a wavelength selection. Now it is 1310. You can change it to 1550. It's a 1550 now. Low is that it is in the lowest power point, and then you can, your backlight is then you can convert from dB to milli nanowatt to dB. Then it's zero setting. So this is the power meter. We'll be using this for the experiment rather than using the details of this kit. We'll start the experiment by making the basic connections, and as you know, this is the optical fiber patch code. It's a SAC patch code, and here you have two ferrules at the end. So in an early experiment we have demonstrated how to couple light into an optical fiber. So this is a single mode optical fiber, 9 micrometer core diameter. 9/125 micrometer is the specification for this single mode optical fiber. So in an older experiment we have shown you how to couple light into a single mode fiber, and if you have seen that, you will remember that it was slightly a laborious task getting the light to focus into the optical fiber and making it go through the optical fiber. It's 9 micrometer opening, right? So it's very difficult to focus light into the optic fiber and make it propagate. So here we have something much more similar. We have a connector, we have ferrule like this. So all you have to do is you have to connect the optical fiber into this particular slot. So before doing that, optical fiber is highly allergic to dust, as in any amount of dust in the fiber tips can really damage the fiber and the lasers also. So you have to make sure that you properly clean the fiber before making each connection. For clean the fiber, use something known as a fiber cleaner here. It's basically something like a tissue paper which is rolled in, and you can like pull it like this. So you take a fresh patch and then you pull down like this. You take it up, pull down, push up, pull down, push up, like. So you have to do it in one direction and you like change the direction which you are doing it. So now that this fiber tip is cleaned, I think we have demonstrated this particular cleaning process in another experiment video before. So now this tip is clean. You can take off this cap and then put it back, push it in like this. Should go in with a tick sound. So if you can hear the sound, yeah. So care should be taken that whenever this laser is always kept closed so that no dust accumulates on the laser output. So the fiber has gone in. So we'll see the power that is coming out of this particular laser. So this is the other end. Other end also needs to be cleaned. So you do it a few times, and then once it is cleaned, you can connect it to this power meter here. And you can control this kit from this PC. There is a software that is given for that. This is a lighter software. So you can shoot it up, and here you have the laser controls. So as you know, there are 4 IR lasers and one visible laser. So visible laser cannot be used in the experiment because EDFA works in in the 1550 nanometer range. So we have individual control for each of the lasers. If you can see the mouse, this is the control for 1510, 1530, 1550 and 1570. You can turn off the other lasers other than the one which is relevant, 1550 in this case. So what is this frequency? So there is of course not the laser frequency. Laser is lasing at 193 point something terahertz, right? So this frequency is the modulating frequency. So there is a provision to modulate the laser light that is coming out of your laser. This is for communication purpose. You can get a modulated signal. Now in this case we don't want any signal, any information to be modulated in the laser light. So we keep those in the continuous mode of operation. So what we have is a continuous laser without any modulation. Okay. So this duty cycle kicks in when we have a modulation. Okay. So it's like how much is the duty cycle you want to use for the modulation. So in this continuous mode there is no duty cycle as in. And then we have the laser power section here. So laser power can be increased in steps of 1 up to step 60. So there is no current, there is no equivalent current that is given. Instead you get step sizes. So within each step you will be increasing the current which is driving the laser in small steps, and we can see the output in the power meter. Of course, as the current increases, the laser output increases. So the laser characterization will be covered in another experiment video, which probably I think it should be done in the next week or something. So that's all that is here, and here is the detector section. If you have the detector connected, so what you have is the detector output. Here here it automatically does whatever is coming in this PD, and if you connect it here, it will be detected in the channel 1 or channel 2 of the DSO. There is a software DSO that is available, which makes use of this communication links. We will go back to our experiment. So here, if you have the detector being used, then you will get the microwatt, how much microwatt is falling in each detector in this particular boxes. So that's basically the software for this particular experiment, software section of this particular experiment. I will go back to and see how much power we are getting for a step 30. So we will keep the laser power in step 30, and let's see turning it on. Okay, let's start the experiment. So here you can see that there is a LED indicator here that goes on. So you can see that the laser is on now. So it is highly, you are not expected, or you should not look into the laser light because it can harm your eyes, but it's like almost 0 milliwatt only, means that we are probably safe, but it is always it's highly recommended not to be looking into it. Now you can see the power readings here is minus 23 dBm, so that's step 30. So I just stop this and I'll increase the power level to step 50 or something, and you can see that you can see that, and turn it on, you can see this is almost minus 1 dBm, and we'll see how much is the maximum power that is available. We'll put step 60 and start the experiment. So we are getting around almost 0 dBm. So almost 0 dBm is 1 milliwatt of power. That is almost the rated output of this particular laser. Now I turned off the laser, so the power has gone back to 0. Now we will see how the connection is done. Okay, so you can see from the connection diagram that the laser should be connected to the EDFA input. So I'll take this. There's a notch in this. There is a notch in this ferrule. You can see this notch. That notch has to go in. There must a corresponding hole there. So I have to connect it like this. So this is the connection. You basically have connected the laser to the EDFA now. Now I'll show you the connection setup of the EDFA as such. I'll remove this for better visibility. I'll cap. You have to always cap the fiber once you are done with it. You cap it like this. Okay. Now I'll show you how the internal connection is made in this particular section. As you can see, it is marked ER3+ here. This is the EDFA there. the EDFA one end is here and the other end is here. Okay, so below this there is a EDFA that is around 10, probably 10 to 20 meter, which is wound inside this particular grid. So it runs from here to here. So you have to give the input at the input end of EDFA, and the signal propagates through this. And here we are using a backward pumping method. So the pump signal will traverse in the direction opposite to that of the signal. So the signal is passing through this way, okay, from this erbium doped fiber to this end, that is through the erbium doped fiber. So basically this entire section is the coupler. Okay, it's a WDM coupler, wavelength division multiplexing coupler. So it is used for multiplexing two different wavelengths. So which are two different wavelengths? One is a communication wavelength, that is a signal wavelength, and the other one is the pump wavelength. Pump is, as you know, the pump is at 980 nanometer and the signal is at 1550. So you need a wavelength division multiplexing coupler for coupling these two together. So this is the WDM coupler, and this is the common port. Okay, this is one input. So if you can see this this element independently, this is one input, this is another input, and both of them will combine together and come out through this. If you are giving signal from this port and this port, it will come out through this. But it's a bidirectional device, so you can give an input from here, then it will, if it is 1550, it will come out through this port, and if it is 980, it will come out of this. Okay, so again, as it is bidirectional, what we are going to do is we are going to give 980 nanometer pump in this port, so that 980 nanometer pump will go in this way, it will go here and then traverse the EDFA in the reverse direction to the signal like this. Okay, so there is an internal isolator for protecting the light for protecting or for preventing the pump from going to the sources. There's an internal isolator inside this. The signal pathway is going to be in this direction. Signal is going to traverse here, then from there to here, and there to here like this. Okay, there to here like this. Okay, and the pump is going to go from here to here, and then here. Okay, so that's the signal and pump propagation pathways. And here where is the pump? So pump laser is here. So it's given very close to the EDFA itself. Now you can see that this section, this is the pump control. But there is a software control also for the pump, which can be seen the screen. Probably will show later. And the laser out that is coming out of a connector is being coupled out through this fiber like this, and you have to connect this end and to clean the fiber first. This EDFA pump laser is having much more power because it is acting as a pump, right? So it has around 100 milliwatt of power, almost 20 dB power that is being output of this particular port. So this special care has to be taken about the laser safety in this from the laser that is coming out of here, and also you have to make sure the laser is very clean. So if there is a fiber, if there is a dust particle in the fiber tip or something, there's chances that it can get burned and destroy the fiber end. So special care has to be taken about this particular laser and its output and its corresponding outputs. Signal has to be given to this end of the fiber, right? So you have to the signal has to go to the input end of erbium doped fiber amplifier. Now that you are done with familiarizing with the kit and the basic circuit diagram, basic connection diagram, now we'll see how the actual experiment is done. Okay, so we'll start the experiment with characterization. Okay, so as in most of the other experiments, we have to characterize the laser first. You have to characterize the pump laser and the signal laser. Of course, there are two of them, and then you have to characterize the coupler that is here. Okay. Characterization is pretty simple in this particular setup. As you know, there are 60 steps in which you can change your laser power. So you change it from 0 to 60 and note down the corresponding power measurements. So laser is a threshold device. So as you increase the current, so with each step the current is getting increased. You increase the current, you see that the output light increases, and there is a threshold in which it starts to increase substantially, and beyond which it is a linear response from there. So that is the characterization for both lasers. So in case of the signal laser, what you have to do is you have to put in the continuous mode and then take measurements from 0 to 60 and note down the corresponding measurements in the power meter. You have to see the power meter readings corresponding to each step. So unfortunately, they have given only step measurements. They have not giving the actual output power measurements. So you have to use a power meter for getting those values. The same goes for the pump laser also, 980 nm pump laser. The only difference is that the signal laser will max out at 0 dBm, and the pump laser will go around up to 100 milliwatt. That's around 20 dBm. So it's actually slightly more than 20 dBm, I think. So you have a higher power coming out of pump laser. You have to characterize both of them. Okay. So basically, what you are going to do is you are getting the x and y axis of x-axis of your experiment in this characterization setup. So once you are done with the characterization of the laser, you have to move into characterizing the coupler. Okay. So this is where it gets a bit tricky, this experiment. So there are different components that is present in the link, right? So basically, what is gain? Gain is the total output in dBm minus the input in dBm. That is as simple as that. It becomes complicated by the fact that there are multiple other components which is causing a loss in the output before reaching the reaching the detector or the power meter. Okay, so these losses that is incurred within the link are actually compensated by the gain of the EDFA, right? So the gain of the EDFA has to be high enough to compensate for all these losses and still provide enough gain for the signal. So the net gain of the EDFA is actually the output power in dBm minus the input power plus the total amount of losses that is incurred within the link, right? So we have to characterize each component in the link to get to know how much loss is incurred in each of the component. Add those losses to the final gain you are getting. Okay, so we will get the net gain. So that is how ideally that's how the experiment needs to be done. But in this experiment, we are slightly doing a shortcut which will be described later. But for the time being, we will show you how to characterize the coupler. Okay, so characterizing the coupler or almost any other optical component is very simple. All you have to do is give the input signal, give a good optical laser input to the input part of the device, and take the output. Okay, you are characterizing this for the attenuation. Okay, just for attenuation characterization, you are doing this. So you have the input, you know the input power levels, and you know the output power levels, and you can easily calculate the loss, right? So that's how you do that. That's exactly how you do that. You have to do that for the coupler. So coupler, in case of WLAN coupler, is slightly complicated by the fact that you have multiple wavelengths that is going in. So as you can expect, we'll see in this kit here now. We'll see how it is actually done. So we'll take the laser output from the 1550 laser that is here, and you connect it to the COM port. So now that we have connected the laser 1550 laser to the COM port, we expect the output to be coming from this port, which is the 1550 port. So this is a WLAN coupler. It will make sure that there is no signal that is going to the 980 laser, because as it is a WLAN coupler, it will couple this light in this way only. Okay, it won't go in this 980 laser. So similarly, if you have a 980 input here, it will go straight into the 980 port and not through the 1550. Okay, so if there is a light that gets leaked from 1550 port to 980 port or vice versa, we call it crosstalk. Okay, so basically we can characterize the crosstalk and attenuation of each channel of the WLAN coupler in this step. Okay, so we have connected the 1550 laser to the COM port, and we can take the output from this 1550 port. So I haven't turned on the laser, so the power is still 0 dBm. I'll keep it here for better visibility. So it is minus 1.07 dBm. Okay, so this is the problem, right? So we don't know how much power is being sent. That is why we should always characterize the laser first, and the 980 laser. So the first step of doing this experiment would be characterizing the laser 1550 laser here, and then characterizing the 980 laser here, and then only you can do this characterization experiment. But as we have already seen the last step, the power was less than this. It was around 0 dBm. So now we have 1.2 dBm. So you have a loss of around 1 dBm. So that is the loss that is provided for 1550 channel by this WDM coupler. Okay, we call it the insertion loss. So insertion loss is the loss incurred in this link just because that particular component is inserted in between the link. Okay, so that is the insertion loss of 1550 nanometer. Similarly, you can find the insertion loss of 980. So for that, what you have to do, you have to connect 980 either here or here. It's a bidirectional device, so you can connect it either here or here. So once you connect the 980 either here, let's assume that you are going to connect 980 here. So you will get an output here. Okay, so that will also be attenuated by a factor, and that is going to be the insertion loss for 980 nanometer. Okay, so for finding the attenuation or crosstalk, you have to give 1550 here and see how much output is coming out of the 980 port. Well, we'll see that right away. So we are going to turn off the laser now. Laser is off, and we'll make the change the connections now. So we'll take the output from the the 980 port like this. Okay, now we'll turn on the laser again. So 1550, we are sending 5050 laser to this WDM coupler COM port and see how much power comes out of the 980 nanometer port. Okay, we call this the crosstalk because nothing is expected to come out of the 980 port, but still because of the coupler imperfections, we might have some output that is coming. So we are turning on the laser now. We are turning on the laser in the screen. So we'll see how much is coming now in the power meter. The power meter will see how much it is coming. So it's around minus 24 dBm that is coming. So we are sending 0 dBm power and minus 24, few microwatts of power is coming out of this port. So that means that there is a measurable crosstalk that is happening in this particular WDM coupler, but it's okay. It's like minus 25 or minus 24 dB less than that of the other channel. So probably for this experiment that is all right. So we'll carry on with that. So in the next step, what you have to do is you have to characterize the WDM coupler with 980 nanometer. Okay, so that will do next. So for that, we will turn off the laser again. We'll turn off the laser and we'll change the connection. So the input now gets changed to 980. So you can cap this and keep it away, the 1550. So this is the 980 laser output. This is 980 laser output. You are going to give that output. First we'll see how much is the maximum power that is coming out of the 980 nanometer laser. Okay, so we'll clean that. So it's very important that you clean the fiber, especially the high power output fibers. You clean it very properly, and then you connect it to the to this port. So basically, for the WDM coupler, you are giving the 980 nanometer to the COM port and see how much is coming out of the power meter. So, but before that, you have to know how much power is coming out of the 980 nanometer laser, right? So we'll connect that straight to this power meter first. So you'll cap this for the time being. So you connect the 980 nanometer laser straight to this power meter, and we'll put maximum power. We'll put step 60. Step 60 in this. So you can see that this is 980 nanometer pump laser. We are keeping it at step 60. So you can see that this is the 980 nanometer pump laser control. We are keeping, there's no modulation options for that, and we're keeping it at the maximum power of step 60. Okay. Now we'll see how much power it is getting. We are getting in the power meter. So we are turning the laser on now. We have turned it on now. So you'll see how much power is coming now. So it's 21.57 dB. So it's more than 100 milliwatt of power that is coming out of that. So you will remember the value 21.5. Now we'll see how much power is getting attenuated because of the coupler for 980. For that, what you have to do is we'll stop the experiment again. So we have taken the connection out and we will connect it to the input port, the COM port of the coupler, okay, the common port of the coupler, and then you see the how much is the output. Again we use the power meter for that. Okay, now we'll turn on the 980 with the maximum power. So maximum power, as you remember, is 21.54. So we'll see how much is coming now as it passes through the WDM coupler. We are getting only 19.2. So that means there is some significance, almost 19, right? It's almost 19 now. So almost 2.5 dB power is being lost in this particular setup. It's actually decreasing a bit. So that means that this WDM coupler gives higher attenuation for the 980 nanometer laser. So you have to note down this value, so that these are the losses that is incurred in the optical link, additional to the actual fiber losses. So your actual gain of the EDFA is going to be the output power in dBm minus input power in dBm plus these losses. Okay, so that's what it is. So I'm going to turn off this now. We'll go into the actual experiment. Now that we are done with the characterization, we'll move into the interesting part of the experiment. We'll do the actual amplification experiment. Okay, so for that you have to do the setup first. So you take the laser output from the 1550 as usual using this fiber. You connect it to the EDFA. You connect it to the EDFA like so. So now the 1550 laser is connected to the EDFA. From the EDFA output, you have to connect it to the WDM coupler. So there is no internal connection here. So you have to take a passcode and connect it to this coupler. So basically, it's two different entities. This is the coupler and this is the EDFA. You are connecting the EDFA to the coupler using this particular fiber. Okay, the EDFA output is connected to the coupler using this. So now we have your signal coming through this fiber, passes through EDFA and coming to the common port of the coupler using this fiber. Okay, now the output of this particular 1550 wavelength can be taken from the output port. This is the output port, the 1550 output port. From the 1550 output port, you are taking the output, and of course the output is to be measured, and we give it power meter like this. So that's the connections. And okay, of course the most important connection we forgot. We had to pump the laser. For that we have the pump that is coupled here. Pump fiber patches here. We have to connect it to the 980 input. So I'll explain the connections once more. The laser light at 1550 is taken from this input, this laser output, and then connected to the erbium dot fiber amplifier here. So there is a erbium dot fiber amplifier residing beneath this particular block, and the signal reaches here and then gets passed to the WDM coupler block using this passcode. So the signal reaches here, and from there the signal gets routed to the 1550 port, that is this. So you get routed internally through this port to this output port, from where it is connected to the power meter. So from where it is connected to the power meter here. Okay, now for the pump laser, the pathway is like the pump laser is residing below this particular port. From there you are taking this laser output through this particular fiber to the 980 nanometer port of the WDM coupler. and the pump goes in the backward direction, in the other direction, the opposite direction to the signal. So the pump goes from this port to the common port in this direction, the other direction, traverses the this particular passcode in the other direction, and then traverses the erbium of fiber in the backward direction like this. Okay, there is a isolator here for preventing the high pump power to leak into the input laser. So this is the basic setup we have to use. Now we'll see whether we are getting gain using this setup. Okay, as a trial case, we'll put maximum power through the 1550 laser, and we'll put maximum pumping also. Okay, so both are at 60 step 60. Okay, so that's as you remember, this step 60 of the 1550 laser corresponded to around 0 dBm, right? Now we are going almost 100 milliwatt of pumping. We are giving almost 100 milliwatt of pumping. Now start the experiment and see how much is the output we are getting. So starting the experiment now. So we are getting almost 4.8 dBm of output. That means you have a gain of around 4.8 dBm because your input was around 0 dBm, right? So that is the base gain you are getting, but it's actually over and above the losses that is incurred in this particular setup, right? So if you remember, you had at least 1 dB of loss in the WD coupler just for the 1550. So your gain is easily more than 5 dBm. But this is not an ideal case, as in we are giving too much of power. We are giving 0 dBm of power in this particular case. So this is not a small signal scenario. Okay, so next step in our experiment is to see how the EDFA gain changes when you change the input signal and the pump signal. Now that you have seen the EDFA gain for a single input and a single pump power, we'll see how the gain changes once we vary these parameters. So which leads to the signal and pump saturation effects. So as you remember from the lectures, the pump saturation happens if you are giving too much pump and there is not enough erbium ions in the ground state for absorbing this. Your gain is not going to keep increasing linearly like this. It is saturated because of the lack of erbium ions in the ground state for absorbing this pump power. So which leads to the decrease in gain. The gain eases off, and that causes the pump saturation. In case of signal saturation, what happens is that the input signal that is coming should be too high, that there is not enough population inversion for sustaining that kind of a high output in the laser. So if you keep increasing the input signal, it will become tough for the EDFA to laser to provide that much output power because of the lack of inversion, because all the inversion is getting eaten up by the incoming signal. So this is the phenomenon we are going to observe in this particular experiment. So we'll see a few of the results now. Now that we've seen a single case of EDFA amplification, we'll see how the input and the pump saturation is affecting the outputs. Now I will start the experiment with pump saturation. Before that, I'd like to point out that whatever values you are going to see here is actually not exact the gain you are getting, because the coupler losses are not added in this particular case, right? So what I am going to show is that we will turn on the laser to show you some values, and then turn on the pump power will show the amplified values. So the difference between them will give you a gain, but that is not exactly the gain because the coupler losses are not taken into consideration for this particular case. So still we are showing this experiment just to give you an idea about how this experiment is done. For getting the actual curves, you have to add the losses, the coupler losses and other losses to the equation. Okay, so this is just a quick view of how the processes comes in. So we start with the pump saturation. So we'll keep the signal level around some 45. I'll start the experiment without the pump. So without the pump, let's see how much power is coming. So without the pump, we are getting around minus 19 dBm. Okay, so it's not exactly, say if you have directly connected this 1550 to the power meter, you would have gotten a higher value. But now that we are connected to the EDFA and there is no pump given, there is the signal is getting absorbed by the EDFA RPM dot fiber, so there is a high loss there. Okay, so this is not so it's not exactly the gain you will be getting here. Now we'll increase the pump from 0 to 60 in steps of 10 or something. So there, it is interesting note that as laser is a threshold device, the laser gets turned on around after 25 step 25 only. Okay, so 25 to 30, 30, 33 of that time means these lasers are turning on. So there's no point in taking measurements below 25 and all, but still we'll take a few measurements and see how it fares. We keep the pump power 10 and see output. So again it's still minus 19. That was as if there is no pumping. So minus 19, and we'll keep it at 20. I'm expecting, we should expect it to be around minus 19 again. So it's minus 20 actually, there's more losses. And we'll keep it we'll keep it in step 30 and see. So it comes around minus 16. So we have started to get some gain, as in the input was around minus 19 and we're getting minus 16, right? So we are getting improvements in that sense. So we'll go to minus 40. So yeah, now we have very serious gain, like minus 1 you are getting. So almost 18 dB of difference you have here. So putting step 50 you have 2 dB. So it's positive 2 dB, and then step 60 you have 3.6 dB output. So so this won't give you the graph, as in, I mean I will flash the graphs, but this won't give you an idea of how the pump saturation is actually kicking in, because the values in dB, and then the steps, the laser power doesn't change linearly with the steps sometimes. So but still we can understand that with more pump power we could get more laser output. And if you document all these values and we'll take and draw the graph, we'll get a linearly increasing and then saturating output. Okay, so that is the pump saturation. Now we'll do a similar thing with the signal. So you have to keep the pump at a reasonable level of step 50. Step 50 is quite good, and you have to increase the signal from around 0 to, let's start with 0 to 60. So so pump is there. Now just with the pump, right, the input is at 0 dBm, I mean is at 0 step. Now just with the pump you have minus 9 dBm. This is because of the spontaneous emission that is happening within the EDFA. So and as we know, the RBM ions are the excited state, they spontaneously come down emitting a photon, and that all contributes to almost minus 10 dBm. That is quite some power actually. So this is actually a noise source in the EDFA, which we will learn later. So we'll keep on adding the signal. So again, signals laser also turns on only around step 25, 28 or something. So here also I am not expecting much change. So it's again minus 10 dBm. Minus, we'll see minus 20, step 20 is shouldn't change much. Should be again minus 9, and step 30 we should expect some changes at least. It has become minus 8 now, so slight changes are there. We'll increase to 40. Let's see how much it is. Now see, there's a drastic change now. We are getting almost minus 1 dBm output power. Okay, so and we'll go to 50, step 50. So it's minus 1 become 0.4. So with the 10 step increase, you are getting only 1 dB increase. From step 20 to step 30 to 30 to 40, you got almost 8 dB of improvement. From 40 to 50, you got only almost 1 or 2 dB of improvement. So that itself shows that there is some kind of saturation happening with increased signal. So again, we'll start with, we'll check out with 60, and here only barely any improvement, 0.6 it is. So not a lot of improvement. So it is very evident that the signal actually saturates the gain of the EDFA. So this is the experiment. So we'll show you some results also if possible. So that is the experiment for this week. So you would have learned the theory of EDFA, how it works, how the population inversion happens, what are the important parameters that affect the gain, etc. In the experiment, in this experiment, we saw how to get a EDFA system going, how to get gain out of it, and how the input and the pump saturates the gain of the EDFA system. So that is pretty much it for the week, and I especially thank Nirjar here for assisting me with the video. So I expect you guys love the experiment setup. That's this for the week. Thanks. Enjoy.
Enjoy, guys. We love your questions.